Hello, my name is Asa Williams, and this is my Lab 3 report on orbital motion and gravitational lighting using VPython. In this lab, I analyzed the motion of a star orbiting a black hole in order to estimate the black hole's mass. The star's position data was generated by the simulation and was unique to my program through an email-based random seed. In the second part of the lab, I simulated the motion of a spaceship near a planet and a moon. By calculating the gravitational forces between objects and using Newton's second law, I determined an initial velocity that allowed the spaceship to move in a complex orbit influenced by both bodies. The goal of part 1 was to determine the mass of an unknown black hole located at the origin. The star orbiting the black hole had a mass of 2 times 10 to the 30 kilograms. The simulation generated the x and y position coordinates of the star at regular time intervals. The time between each data point represented 1 Earth day. Using this position data, I calculated the velocity and acceleration of the star as it moved through its orbit. From the acceleration, I calculated the net force acting on the star using Newton's second law. Because the only force acting on the star was assumed to be gravity from the black hole, I could then use the gravitational force equation to solve for the unknown mass of the black hole. Two main physics principles were used. The first is Newton's second law, which states that F is equal to ma. The second is Newton's law of universal gravitation, which describes the gravitational forces between two masses. According to this equation, the force between two objects depends on the gravitational constant g, the masses of the two objects m and the distance between them r. Since the star's mass and its distance from the black hole were known, and the net force was calculated from the star's acceleration, I could rearrange the gravitational force equation to solve for the mass of the black hole. Each time the calculation loop ran, the program produced a slightly different estimate for the black hole's mass. These small variations occurred because the acceleration and force values changed throughout the star's orbit. To determine a single best estimate, I averaged all the mass values calculated during the simulation. The average mass I found for the black hole was approximately 1.84 times 10 to the 34 kilograms. This result represents the mass that would produce the gravitational force necessary to keep the star moving in observed orbit. Newton's second law can also be written as net force is equal to the rate of change of momentum. Momentum is defined as the product of an object's mass and its velocity. The rate of change of momentum describes how quickly the momentum changes over time. The net force acting on the object causes this change. When analyzing motion, it is useful to think about the force in terms of components. The component of force parallel to velocity changes the object's speed. The component of force perpendicular changes the direction of motion. In orbital motion, the perpendicular component is especially important because it continually redirects the object's path, producing curved motion around another body. That's what keeps the star orbiting the black hole rather than traveling in a straight line. In the second part of the lab, I simulated a system consisting of a planet, a moon, and a spaceship. The planet was placed at the origin and remained stationary. The moon started to the right of the planet and initially moved upward, creating a circular orbit around the planet. The spaceship began on a hill 100 meters above the surface of the moon on the side facing the planet. During each step of the simulation, the program calculated all gravitational forces acting on the moon and on the spaceship. The moon experienced gravitational forces from the planet and the spaceship, while the spaceship exerted gravitational forces from both the moon and the planet. Using these, Newton's second law was applied to update velocity and position of objects over time. To produce a complex orbit influenced by both the planet and moon, I experimented with different velocities. The velocity that produced a stable orbit was the Vx equal negative 220 meters and Vy equal to 1250 meters. With this velocity, the spaceship followed a curved path that was affected by the gravitational pull of both the moon and the planet. If we wanted to model the motion of the entire system realistically, we would need to include every gravitational interaction between all objects. This would include the black hole, the star, the planet, the moon, and the spaceship. Each object would exert gravitational forces on every object, meaning the simulation would need to calculate many force interactions at each time step. In practice, the most dominant interactions would usually come from the most massive and closest objects. In conclusion, this lab demonstrated how Newton's law of motion and universal gravitation can be used to predict motion. By analyzing the motion of the star, I calculated the estimated mass to be 1.84 times 10 to the 34 kilograms. In the second, I calculated gravitational forces between multiple bodies to determine an